Welcome to Go Lesson 33. Today we work with databases using SQLite. We cover connecting, CRUD, migrations and advanced queries. Everything uses a pure Go SQLite driver. No C compiler needed. Let us start with the basics of connecting to SQLite from Go. Go's database/SQL package provides a standard interface for working with any SQL database. You write the same code whether you use SQLite, Postgres, or MySQL. We import database/SQL for the standard interface. The _import of modern c.org/SQLite registers the SQLite driver. This is a pure Go implementation, so there is no C dependency. sql.Open takes a driver name and a data source. For SQLite, the data source is a file path. This creates the file if it does not exist. We always defer db.Close to release the connection when main returns. db.Exec runs SQL that does not return rows. Here we create a users table with 3 columns, an auto-incrementing id, a name, and an email. For inserts, we use question mark placeholders instead of string formatting. The driver substitutes the values safely, which prevents SQL injection attacks. QueryRow fetches exactly one row. We call scan to read column values into Go variables. If no row matches, scan returns SQL, no rows. After inserting the second user, we use db.Query to fetch all rows. Unlike QueryRow, this returns an iterator. The rows.Next loop advances to each row. Inside the loop we call rows.Scan to read columns into variables. Always defer rows.Close to release resources. Let us review the complete code before running it. The pattern is straightforward. Open a connection, create a table, insert rows with placeholders and query them back. Now let us run the program and see the output. Each insert is verified immediately. The final listing shows both users stored in the SQLite database file. Now let us implement full CRUD operations: create, read, update and delete. CRUD is the foundation of any database application. We will verify the result after every single mutation. First, we define a printall helper function. This queries every row from the to-dos table and displays them with a checkbox format. The status variable shows an X for completed to-dos and a space for pending ones. This makes the output easy to read at a glance. We call printall after every insert, update and delete so viewers can see the database change in real time. For this demo, we use an in-memory database with the memory connection string. Everything lives in RAM and disappears when the program exits. The todos table has an auto-incrementing id, a title, and a done column that defaults to false. We insert 3 todos in a loop. db.Exec returns a result interface with 2 useful methods, LastInsertId and rows.Affected. LastInsertId gives us the auto-generated primary key, which we print to confirm each insertion. Now we call printAll. All 3 todos appear with empty checkboxes since done defaults to false. The update statement marks the first to-do as done. Rows.Affected returns the number of changed rows, which should be 1. After the update, notice the first to-do now shows an X in its checkbox. The other 2 remain unchanged. Delete removes the second to-do. We verify that exactly 1 row was affected. The final printAll shows only 2 todos remaining. This confirms all 4 CRUD operations work correctly. Let us review the complete code. The key takeaway is that db.Exec handles all mutations and returns a result for verification. Now let us run the program. Watch the output carefully. Each operation is followed by a full listing that proves the change took effect. Next, let us build a migration system to manage schema changes over time. In production, you cannot just drop and recreate tables. Migrations let you evolve the schema incrementally, while preserving existing data. We use PRAGMA user_version, a built-in SQLite integer that persists with the database file. It acts as our schema version counter. The getVersion function reads the current version. setVersion updates it inside a transaction so the version always matches the applied migrations. We define a migration struct with a name for logging and an up function that receives a transaction pointer. Our migration slice contains 3 schema changes. Migration 1 creates the users table. Migration 2 adds an age column with alter table. Migration 3 creates an index on the email column. Each migration builds on the previous one. This is the power of incremental migrations. You can add columns, create indexes, or restructure data one step at a time. The run migrations function is the core of our system. It reads the current version and loops from there, applying only new migrations. Each migration runs inside a database transaction. If the migration fails, the transaction rolls back, and the version stays unchanged. This keeps the database in a consistent state. After applying each migration, we update the user_version inside the same transaction. This guarantees the version and schema are always in sync. We call run migrations twice to demonstrate Idempotency. The second run reads the version, sees it is already at 3, and skips all migrations. Finally, we insert a user with the new age column to verify the migrated schema actually works. This pattern scales well. As your application grows, you just append new migrations to the slice. Let us review the complete code. Notice how the migrations are self-contained functions. Each one describes a single schema change. The bat review shows 4 pages of code. Let us page through it. Now let us run the program and watch the migrations execute. The first run applies all 3 migrations in order. The second run is a no-op, because the version is already current. The final output confirms the user was inserted with the new age column, proving our schema is correct. Finally, let us explore 4 advanced topics: prepared statements, nullable columns, aggregate queries, and transactions. These are essential patterns you will use in any real database application. We start with a products table. Notice the description column has no not null constraint, which means it can store null values. The create table uses real for the price column. In SQLite, real stores floating point numbers. db.Prepare compiles a SQL statement once. We call tx.Exec in a loop to reuse the same prepared statement for all 5 inserts. This is more efficient than calling db.Exec 5 times. Some products have descriptions while others pass nil. Go's nil maps to SQL null. This is why we made the description column nullable. The product data includes keyboards, mice, monitors, headphones, and webcams with prices ranging from $50 to $300. Now we query the products back. The key here is sql.NullString. Go cannot scan a SQL null NUL into a regular string, so we use this special type. NullString has 2 fields. String holds the value, and valid tells us whether the value is null or not. When valid is false, the column was NUL in the database. We display n/a as a fallback for missing descriptions. Aggregate functions like count and sum compute values across all rows. Since they return a single result, we use QueryRow instead of query. db.Begin starts a transaction. Everything between begin and commit is treated as a single atomic operation. We apply a 10% discount to all products. If the update fails, we call rollback to undo everything. This protects against partial updates. If everything succeeds, commit makes the changes permanent. After committing, we query the prices again to verify the discount. Let us review the complete code. This is our longest example, with prepared statements, null handling, aggregates, and transactions. 4 pages of code. Each section demonstrates a different advanced pattern. Now let us run the program and see all 4 patterns in action. The initial listing shows 5 products with their prices. Nullable descriptions display either the text or n/a. After the transaction commits, every price drops by 10%. The new total confirms the discount was applied across all products. Let us recap what we covered. sql.Open connects using a pure Go SQLite driver. db.Exec and db.Query handle writes and reads. Migrations track schema changes with PRAGMA user_version. Thanks for watching. In the next lesson, we will learn testing in Go.